Basic electricity. Basically, what is electricity? Electricity is our product, what we sell, what we charge our customers for. So what is it exactly? You can't hear it, see it, smell it, but it definitely exists because we all get paid by it. We see the effects of it. So we need to have an understanding of what it is, and that's what we're going to attempt to do today. Bear with me, we will eventually get there, but we are going to venture all the way back to 7th grade physical science class. We're going to go back and look at the molecular structure of things. Don't tune me out just yet. We're going to make it Lyman simple, okay? So let's look at the atom. Electricity is a form of energy that begins with an atom. Basically everything does. Everything's made up of atoms, and we're going to break that down just a little farther to the components of the atom. So let's look at those things. So what are atoms made up of? Well, we have inside the nucleus in the center, right here in the center, it's what we call neutrons. Now everything has a charge, and basically the neutrons have a neutral charge. That's easy for us to remember that. Neutrons, neutral, N and N. And also it's the neutrons are the heaviest part of these elements, these components, and they're about 1,840 times heavier than the other parts, and they have a neutral charge. Also, we have inside the nucleus protons. Protons have a positive charge. They're a little bit lighter, and they're there in the nucleus with the neutrons, okay? And then also on the outer orbits out here, we have what we call electrons. Now, electrons have a negative charge. We have positive charge and neutral charge protons and neutrons inside the nucleus. And on the outer orbits, orbiting around here, around the nucleus, we have electrons, and they are negatively charged. Okay. All right. So electrons are what makes the lights come on. When we say that we sell electricity or we measure electricity and current, we're actually selling or measuring the movement of these electrons down a conductor, okay? And when the lights come on, that's the effect of those electrons moving through that conductor and exciting it and causing it to glow and stuff like that. That's a little deep, but that's what it is. All right, so conductors. So if we have the electricity is the movement of electrons, what are conductors? Conductors are materials that have lots of free of electrons. There's an imbalance. In that nucleus, in that atom, there is a number relationship between the neutrons, protons, and electrons. So if a material has lots of free of electrons, it's going to have more electrons than it does protons. If they had an even number, they would be bonded or bound together. But since there's an imbalance, say if we had 20 neutrons and 30 electrons, we would have 10 free electrons. And a conductor has lots of those free electrons. It has a lot more electrons than it has protons, okay? Materials that allow the passage of electrons from one atom to another atom are called conductors, and conductors will flow through, current will flow through a conductor. So copper, aluminum are good conductors, good for us anyway. They're better, but definitely those are best for us because of their strength and their cost efficiency and stuff like that, okay? So the movement of free electrons from one atom to another atom is called electric current. And basically what they do, when we excite it at the generation plant, we put a pressure on it, okay? And we cause those electrons to want to move, and since they have a path to move with a potential difference, they will. Electric current is always seeking a path to ground and also always seeking a path to its source. That's what it's wanting to. When those electrons leave the generation plant or whatever we cause this movement of electrons, they want to return back there, okay? And they will return back there through any means necessary. Come down our pole grounds, travel our system neutral, and if you get in series with that, those electrons will flow through you, going back to that source. Electric current will take a path of least resistance to ground. It prefers the path of least resistance to ground. The majority of them will go through the least resistive path, but they will take all path and by any means necessary. Positives attract negatives. When positive attracts negatives, that's what keeps those those electrons bound. If there's one-to-one relationship between neutrons and protons in that protons and electrons in that atom, then they're bound because opposites attract. Positive charge, negative charge, they're holding each other together. But when we have more electrons, those become free because of that attraction. Okay, so if that's a conductor, free electrons, what would be an insulator? An insulator would be a material with very few free electrons. That we come closer to a one-to-one relationship, or maybe that we have more protons than we do have electrons. So those electrons become bound because of their opposite charges and the attraction of that, and then they are bound together, and therefore even if we do put a pressure on them, then they're not able to move. But we can put enough pressure on them to make them move. Probably insulators have a lot more protons than they do electrons, which each actually helps hold them together. If you had 20 neutrons or protons, you had 20 protons and 10 electrons, you'd actually have kind of a relationship of 2 to 1. You'd have 2 neutrons pulling on 1 electron, so that would bind them even more. Okay, so the material resist the passage of electrons. Insulators will prevent the flow of current, and good insulators are rubber, plastic, bait-like, porcelain, glass. There are many others that can be added to the list, but those are the ones that we're most commonly see in the utility industry. Okay, so what is electricity? Hopefully you can answer that question a little better now. It's basically the movement of electrons. A little more technical on the end of that, another end of that, electricity is an electromotive force applied to a conductor to force the movement of free electrons from one atom to another. I already mentioned that before, but it's a term. The terminology is electromotive force. That's what electricity is. This force is created by friction, chemical action, heat, light, pressure, or induction. And we use all of those in our industry. Electric pressure, what is that? The pressure applied to free electrons is called voltage, and that's what we do at the generation plant or distributed generation as well, with solar panels, wind, stuff like that. So basically what we do, we're not creating electricity. We do sell electricity, but we're not creating it. What we're doing is creating a pressure and pushing on those electrons to cause them to move down that conductor, and then at the end result is our consumer members using those. Pressures applied to free electrons is measured in voltage. So that pressure, higher voltage, it all works together there. The electrical symbol for volts is E. And it made it much simpler for us if they would have just used a V, because we understand volt, but they used the E for electromotive force. So an example that we use to help people understand is a simple basic water system. Okay, so we have the water pump here, right here, that creates the pressure. The water's already there. It creates the pump turns and it puts that pressure, and if it has a place to go, it will go, the same as electrons. Okay, the flow of electrons is in a circuit is measured in amperes, or we commonly refer to that as amps. So what do you think the electrical symbol for amperage is? A simple thing would have been to do is to use an A, because we call it amperes or amp, but basically they use the I because it's the intensity in which those electrons move. Makes a little sense once you understand it and once it's been explained to you. So what is an amp? 1 amp is a coulomb per second. 1 coulomb is 6,300 quadrillion electrons that have moved in 1 second. Okay, so if you have 6,300 quadrillion electrons move over a period of 1 second, that's typically measured as an amp. That's a lot. What's a quadrillion? I have no idea. So we can measure that intensity with a water meter, and that's basically what your water meter at your house does. The same as if we used an amp meter to measure the flow of electricity, the flow of water, the flow of electricity. Hope you're seeing the correlations here. So another terminology we need to understand is resistance. What is resistance? Resistance is anything that opposes the flow of electrons. It's a little different than insulation. Insulation is stopping the flow of electrons. Resistance is opposing the flow of electrons. And it could be something as simple as it not having an adequate number of free electrons, or it could be one of those materials that has no free electrons, but we can put enough pressure on it to pry those electrons away from those protons. So it's a little different. We will have current flow with resistance until it becomes purely resistive, but then we can increase the voltage and get it go beyond that limit. Okay, so resistance is measured in ohms. The electrical symbol for resistance is R. Kind of made that one easy for us. We call it resistance, we measure it in ohms, but yet we're using the R as the electrical symbol. So what's the example of that in the water system? Well, basically you'll see here that we have the water pump that's creating the pressure. We have the conductor, the pipe, that's allowing it to go. We have the water meter that's measuring the flow of electricity. And the resistance would be, see here on the end, that you have a smaller pipe. You definitely have less room for it to go. Now the difference in that and the electrical system is that where it's similar but different, where it's similar is we have smaller wire. So definitely a smaller wire is going to have fewer electrons to aid in this conducting, or these electrons going from one atom to the next. So it's the same thing. Smaller pipe, smaller wire, there's resistance there because in the pipe where we differ, it's just not space for them. In the electrical circuit, they're just not available. So there is some resistance to the wire due to the fact that there is the absence of enough electrons. Okay. So let's look at a simple circuit. An electrical circuit follows a complete path return to the source. Okay, so we have a simple circuit, DC circuit. It's a little different than AC, but it helps us to understand how electrons flow. So we have a source here in this battery. We have a positive and negative terminal. We know that those are attracting. So if we have movement or those two connected, they're going to want to go from one to the other. The battery is the source. So we have all this. This is a fuse, that's a switch, and a screw-in light bulb that's screwed in, and it's wired up in series. So actually you have one wire here. Okay, it's one wire going from here all the way around back to the other side. And here it hooks in. The electrons will actually go up through the bulb, across there, and back down, and back around to the other side. So with the fuse in, switch closed, and light bulb screwed in, we attach it to the source. I think we can all agree that the light bulb will come on if the circuit's intact, it's complete. But if I take right here and I unscrew the fuse, the light bulb should go off. If I screw the fuse back in, and then I open the switch, light bulb goes off, right? So I close the switch back in and the light comes back on, and I come over here and unscrew the bulb, okay? Then the light bulb obviously goes off. I hope we would all get that one. Bulb's not connected, it's not in the circuit, definitely it can't come back in. Okay, so now we've screwed the bulb back in, the bulb comes back on. We know that we have current flow because we see the effects of those electrons moving through the light. That makes it glow, and we see the effects of the light. Okay, so the big question here is if we go right here and we cut the wire, does the light stay on or does it go off? And the answer to that question is that it goes off because we don't have a completed path. Okay? So there has to be a path in order for those electrons to flow. The question is on our power lines, when our neutral is down, or maybe our neutral's down, and we know that's our return path. There's always current flow on our neutrals. How do our lights continue to stay on? And basically it's because of all those ground wires, pole grounds that you put on the pole, and all those ground rods that you put down. That completes the path. The electrons will return to the source by any means necessary. They prefer the path of least resistance, which would be our system neutral. If that becomes opened and you bridge that gap, they will flow through you to return to their source. Okay, so if the neutral's down, not connected, it's going down those pole grounds, into those ground rods and into the ground, and returning back to the source through the earth. That's why you should be very cautious of reconnecting that and you getting in series with it. You should wear your rubber gloves. Probably a great idea to kill that out. Okay, so this slide, fixed relationships exist between the current, which is I, the E, which is voltage, and the resistance. So there's a fixed relationship between the current of the system, the voltage of the system, and the resistance of the system. And there's a little math problem, a little formula that we have that we can figure out. If we have two of those, we can figure out the other one. Okay? So I current flow, and the intensity of the current flow through the same resistance changes as the applied voltage changes. So in a simple series circuit, if we increase the voltage, we increase the current. Okay? If we increase the resistance, we lower both of those. Okay, when E, the voltage is held the same, the current changes when the resistance is changed. Okay, so if we add resistance in a series circuit, that definitely reduces our current flow because that resistance is the opposition of the flow of electrons. When I, the intensity, current flow changes, and the relationship and the resistance remains the same, then the voltage would change. Okay. And basically this is the way we keep up with it. It's the Ohms Law wheel. We have voltage on top, we have amperage here, and resistance there. So basically it's simple math. If you have the voltage on the top and you know the current, we can divide the current into the voltage and find out the resistance. And the same thing is we can take the resistance and divide it into the voltage and find out what the amperage is. Or we can take the current and multiply it by the resistance and find out what the voltage is. Okay? So the components of Ohm law is E for voltage, I for amps, and R for resistance. We already talked about that. And there's what I was talking about. Divide the amperage into the current, get the resistance. Divide the resistance into the voltage and get the current. Or multiply the current with the resistance and get the voltage. Okay? That's all you need to know about that. All right, so you try it out. You have a circuit with 6 amps of current and 40 ohms of resistance. What is the voltage? We'll go back a slide and look at that. Basically, we'll take the current and multiply it by the resistance. That's what we have, current and resistance. So what's the voltage? The voltage should be 240 volts. Okay, it's pretty simple. Simple math, simple formula. Here's another one. You have a circuit with 448 amps of current and 10 ohms of resistance. What is the voltage? We'll just do the math again. And we'll do the math again. We have the voltage, which is what we're looking for. And we're going to take the current and multiply it by the resistance. And we're going to take our 48 amps, multiply it by our 10 ohms, and we're going to get 480 volts. Okay? Don't know that you'll use that very much out on the field. We're going to use that that information and that knowledge to help us to understand some other stuff that we will use, but definitely it helps us to understand what's going on out there on the line. Okay? Next slide. So we have another simple circuit. You have a circuit of 10 amps of current and 120 volts. So what is the resistance? A little different here because we're missing one on the bottom. So we're going to take our current and divide it into our voltage and find out what our resistance is. Okay? We'll take our 10 amps and we'll divide that into our voltage of 120 volts. And we will come up with 12 ohms of resistance. Okay? One more time. and we have 6 ohms of resistance and 12 volts. Okay, so now we have the resistance, we have the voltage, we're looking for how much current. So basically the same thing. We're going to take, when we want to find our current, we're going to take our voltage and divide it by our resistance. Okay, so our voltage is 12, our resistance is 6. Divide the 6 into the 12, and we're going to have 2 amps on that circuit. Okay, simple math there again, simple formula. Make note of it, use it where you can or where you need to. Now the power circle. Now we will use this, and you can use this, and this is very beneficial to you to know. Helps to understand this if we understand the Ohm's Law circle. Okay, so here on the top we have the P, that is watts, and we have the I, current, and the E, voltage. One of the ways to remember this is pi, P-I-E. Okay, going counterclockwise, or you could go clockwise as well, wouldn't matter. But PIE, counterclockwise, power watts, amperage I, and voltage E. So power versus energy, what is the difference there? Power equals 1 watt. The power expended when 1 amp flows through 1 ohm of resistance. It takes 1 volt of pressure to push 1 amp of current through 1 ohm of resistance. Okay, I know that's a lot. But that's what it is. Energy. Energy is the average rate at which work is done multiplied by time. Okay, 1 watt hour. The energy expended in 1 hour when the power is 1 watt, measured by a watt hour meter. That's actually what we charge for. If we have 1 ohm or 1 amp going through 1 ohm of resistance for up to an hour, that would be 1 watt hour. And whatever our rate for that is what we would charge for it. The meter keeps up with all that for us. Okay, the components of the power circle there again, E is voltage, I is amp, and P is watts. And we do the same thing as we did with the Ohm's Law wheel. If we know any 2 of those, we can find the other one out by doing some simple math. If you know the current and the wattage, we can take the I, the current, divide it into the watts, the P, and come up with the voltage. Or vice versa, divide the voltage into the watts, and we'll find out the current. If we know the current and the voltage, we can take and multiply those 2 things together and find out what the wattage of that usage of that device would be. A lot of times you'll look at a device, a drill or a hair dryer, a washing machine, a stove, and stuff like that. It will be rated in watts. Okay, it'll be a 1200 watt whatever, and we know that we're going to put 120 volts to that, so we could take and put that into there and find out how many amps that particular device would draw, and then we would know what size wire and then what size breaker to put on that on a simple circuit in our house. Okay, same thing happens out on the power line. So already talked about that. You have a circuit, so let's try it out. So you have a simple circuit with 5 amps of current and 60 watts of power. So what is the voltage? Remember the wheel, okay? So we're looking for the voltage right here on the bottom hand, right, and we have the current and we have the wattage. So we're going to take the current and divide it into the watts and find out what the voltage would be of that circuit, okay? So you have the voltage, we're looking for that. We're going to divide the current into the power. We have 60 watts, we have a half an amp of current, and our voltage is going to be 120 volts. Okay, that's the way that works. So you try that one. It's the same thing here. We're actually going to take our current and multiply it by our voltage because we're looking for the watts, and we have 4 amps and 120 volts, and that is going to equal 480 watts. So if you had a device that was 480 watts and you knew that the voltage, you could measure that, find out what that was. You can divide that into the 480 watts and get the 4 amps. The same thing if you measured the current. Find out you had 4 amps on the circuit. You measured the voltage, you have 120 volts at this device. You can find out what the wattage of that device is. Okay? So there's another one, kind of a little different what we would see out on the power line. You have a circuit with 83,820 watts of power, and 7,620 volts. What are the amps? Figure that up. It's pretty simple, same formula. Voltage divided into the watts, the power. So you have 83,820 divided by 760, 7,620 volts. Do the simple math, and there are 11 amps on that circuit. Okay, so, but we usually talk about kilowatts. So what is a kilowatt? Kilowatt is just like a watt, but it's not a watt. Actually, it is a watt. It's just a whole bunch of them. Just like a watt, this is the measurement of energy. A kilowatt is the amount of energy used divided by 1,000. Okay, so the word kilo right here, the word kilo, kilowatt, that means 1,000. So if we have 1,000 kilowatts, we want to divide that by 1,000. That would be that we would get 1. Okay, kilowatts is the amount of energy divided by 1,000. If we multiply 1 by 1,000, that would be 1,000, and that would be 1 kilowatt. Okay, so it would be 1,000 watts, or 1,000 kilo, or 1 kilowatt. The amount of energy watts used divided by 1,000 multiplied by 1 hour, and that's basically what our meters do. Kilowatts by hour. So figure that. You have 35 amps of current, the intensity, amperage, and 240 volts. So find the kW. What are the kilowatts? We would do kW equals 35 times 240. That would be, and then that would be, we would get 8,400. Divide that by 1,000, and we would end up with 8.4 kilowatts. Okay, 8.4 kilowatts, multiply that by 1,000, that's 8,400 watts. Important factors about power. Everything has an efficiency. You see on the appliances these days that say Energy Star, motors, compressors, stuff like that have an efficiency. The efficiency is the output of a machine divided by the input of the machine. So if we put 100 amps into a motor, we're not going to get 100 amps of work out of it. And there's a way to measure that, and through horsepower and stuff like that. We'll get into that in just a little bit. So that loss there is going to be the efficiency of the motor. Okay, if we put in 100 amps and we get 100 amps of supply into the motor, and we get 90 amps of work out of it, that's going to be an efficiency of 90%. We lost 10%. We have a 10% loss due to the friction of that motor, the insulation in the wires and the windings and stuff like that. And then, so we lost 10%. We actually got 90% out of it, so that motor would have an efficiency of 90%. The output of a machine cannot be equal to the input of the machine because nothing's perfect. 746 watts equals 1 horsepower. All motors are labeled with horsepower, but that doesn't work in our mathematical equations. Somebody figured out that it would take 746 watts to turn a 1 horsepower motor at minus its efficiency. So almost all motors are labeled with horsepower. To find the amps when horsepower is known, you must know the motor's efficiency. For the most part, it's in the neighborhood of about 90%. Usually it's on the nameplate of the motor itself. There was a point in time a few years back that everything, the efficiency of all motors had to be increased. It was a government regulation. They were in the 80%, high 80%, and they had to get them into the 90s. And the way they did that with less friction, better bearings in motors, brushes, stuff like that, and also with better insulation in the wire so that we didn't lose that EMF, electromotive force. But what if the nameplate is missing or doesn't give the efficiency? You see it there in the red circle. This motor has a 93% efficiency. We have to put that in our equation. It's a 30 horsepower motor. They say it's going to use 35 amps at 1765 RPMs. but it has a NEMA rating, nominal efficiency, 93%. And we'll see how that plugs into our equation. So basically we have the same thing here. We have the wattage. We want to know the current draw of this motor. We have the voltage. We know from the power circle that we divide the voltage into the wattage and to find out what the current is. So we have horsepower, whatever it is, 1, 2, 3, 4, 5, times 746, because each horsepower is equal to 746 watts. Okay? And then we have the voltage, say it's a 120 volt motor. We have efficiency of the motor, say it's 90%. And then also there's another little something there, the PF, the power factor. Not going to get into that too deeply today, but the power factor is basically whether our voltage or our current's leading or lagging. That has to be accounted for as well. Now, when your air conditioner cuts on in your house and the lights dim down, that's because the current has outrun the voltage. You have a huge current influx, current inrush, but yet our voltage gets drugged down because we've increased the resistance there. Okay, so that has to be accounted for. It happens definitely at the beginning and the start of the motor. That's one of the things that capacitors correct. They're hooked on there. When there's a deficiency, they discharge and keep that voltage up and try to keep that voltage and current running together. Also out on the lines, our power lines, we have thousands of motors running on our power lines, and that's one of the reasons that we put capacitors on there, to keep that current, keep that voltage running as close to unity as possible. So we can take this equation and figure out basically whatever we need to find out. If you did have the current, you can take and put the current here as well to find out the voltage. But typically if we can read the current, we're going to be able to, the voltage we can read that as well. So most of the time this is the formula that's used to find the current draw. That helps us determine wire size and stuff like that. Okay, so I think we got a math problem here. Let's do this one. How many amps would a 1/4 horsepower single phase motor take at full load if the motor is rated at 110 volts and has a full load efficiency of 85%, which is not very good, and a full load power factor of 80%? Okay, so basically we're going to take our formula. We're going to take that 1/4, 0.25, and multiply it by 746 right here, and we're going to come up with 186.5, and then we're going to take the voltage, 110 volts, 85% efficiency, and 80% power factor. Multiply all of that together, and we come up with 74.8 on the bottom. That's our voltage, and then that's our wattage, and we're going to divide that into our voltage into our wattage, and we're going to come up with our amperage. So a 1/4 horsepower motor rated supplied with 110 volts, 85% efficiency, and a full load power factor of 80%, that motor will draw 2.5 amps. Okay, pretty simple, useful stuff. What happens when the power factor is close to unity? You can go in there and change. You can up your power factor to about 95%. You can increase your efficiency of your motor up to 95%, and this motor will draw much less amperage. You can work that out if you want to. What do you do this problem? Okay, how many amps will a 1 horsepower single phase motor take at full load if the motor is rated for 110 volts and has a full load efficiency of 92% and a full load power factor of 85%? We have 1 horsepower times 746 right here. We get 746. Our 110 volts, our 92% efficiency, and our 85% power factor. Multiply all that together, divide 86.02 into 746, and that motor will pull 8.67 amps. 3-phase. So we have to, you see that the formula is a little different. The formula for full load current of a three-phase motor is the same, except that it has a power factor that it has the factor 1.73, which is ironically the square root of 3, included in the formula. If it's three-phase, we have to account for all three voltages. So we would take 1.73, multiply that times our voltage, our efficiency of the motor, and the power factor. That's the only thing you do to find out the current of a three-phase motor. Only thing different that you do. So here we go. Calculate the full load current rating of a 5 horsepower three-phase motor operating at 220 volts and having an efficiency of 80% and a power factor of 85%. So the same formula. There again, basically we have the 5 horsepower times 746, we get 3,730. We use the 1.73, the square root of 3, because our potential difference is from phase to phase and not phase to ground. We have a voltage of 220 times our efficiency of 80% and our power factor of 85%. Multiply all that together, you get 259, and then divide that into 3,730, and that motor will pull 14.4 amps. Okay, so here's another problem. We have a 10 horsepower motor, three-phase motor, operating at 240 volts and having an efficiency of 85% and a power factor of 60%. Put our formula there. We have 10 horsepower. 10 horsepower times 746, we get 7,460 watts. And then we use the 1.73, our voltage of 240, our 85% efficiency, and our 60% power factor. Multiply all that together, we get 212. Divide that 212 into the 7,460, and that motor will draw 35 amps. So you would need wire big enough to carry 35 amps, and you would need a breaker for that wire to protect it at 35 amps. Okay? Finding horsepower. So we don't know the horsepower of the motor, but we do know the voltage and we do know the current. It's basically the same power circle. We just take and invert it because we're going backwards now. We will take our voltage and multiply it by our current. Multiply it by the voltage, our efficiency of the motor, and also the power factor, and then we will divide it by 746. Okay, there's another simple problem there. You can work that one out. I'll just kind of breeze through it real quick. That's finding the current. You see the 746 is on the bottom, and that ends up being 1 horsepower. If you need to look at that a little longer, you can pause the video. Finding the horsepower in a three-phase motor, same thing there. You just add the 1.73. You got the voltage, the current, the voltage, the efficiency, and the power factor. If it's a three-phase motor, you can still find the horsepower if you can measure the current and the amperage, which if it's running, you can. There again, there's another problem. Let's go ahead and put it up there for you if you need to look at it a little more in depth or want to work it out. You can pause the video right there before the answer is exposed and see if your math is right, and then there's the answer. Okay? A few more useful equations. We're almost done. We got about 4 more slides. Finding the kW of a single phase. Remember, K is 1,000, so you just divide it by 1,000. Okay, so you take the current, multiply it by the voltage and the power factor, and divide that by 1,000. And that would, if it was 25 kW, divide it by so there those are. Find the amperage when kW is known. Single phase kW times 1,000. Voltage, power factor, divide that into that. Three phases, same thing. Okay. Full load amps when kVA is known. That's a little something that we're familiar with. kVA. kVA there again stands for 1,000. The K does. VA stands for volt amps. And that's how our transformers are rated, right? 25 kVA. So basically you could say 25,000 volt amps. So that's the way you would break that out. kVA times 1,000 divided by the voltage, and you would find the amps. Okay, and then you have a three-phase kVA times 1,000. You'd multiply the voltage by 1.73, and then divide that into the kVA times 1,000. So simple math. You could do this program. You can find out what size transformer you would need to supply that motor. Okay. And so you would do the regular formula like you normally would to find out the current of that motor draw, the current that motor would draw. And then you could take kVA times 1,000 and divide it by the voltage and find what size transformer you would need to supply that amount of current. We'll go over this more in detail and in depth in the class, but there's the formula if you need it to do this. The test here at home. Transformer sizing from prior slide. There again, straightforward. You have the 2 horsepower, 746. That's just working the math out for you. That motor will pull 8.12 amps. Then you can take that and try to find the transformer that will supply that much current. So you take the kVA, take a 2 kVA. Multiply the 2 times 1,000 to get rid of the K. That'd be 2,000 amps. And divide it by the voltage, 240. And a 2 kVA will provide 8.3 amps. That should not say kVA. That should say amps. So that would match up. So we would choose a 2 kVA transformer in order to supply that motor, a 2 horsepower motor. This concludes this program. You'll go now and take the quest. You go back to the thinksafety.coop, go back to videos, and under this video that you clicked on to find this, you will click on test and take the test. On that test, just put in your name, first and last name, create a password. That's just in case you want to get back to the test, and then I'll get the results of that.